Hi folks, welcome back to Physics with Captain Rod. I am making this video to help you out a little bit with number 137 in chapter 16. So my first thing to comment about this problem is a bit more complicated than I originally thought. If you read it carefully, it says to find the velocity and acceleration of B relative to A, meaning like if you were in a car here, what would the velocity and acceleration of this be while you're in this car? You know, in a coordinate system here fixed to A, basically is what they mean. So the first thing I would suggest doing here is putting a coordinate system here centered at A. And I'm just going to do a standard right positive coordinate system. Oops. I'm going to draw my coordinate system in green here. So X, Y. And I'm going to put a little x, little y here. I'm also going to put, imagine another coordinate system superimposed right on top of it, a big X, big Y, where the big X, big Y is a fixed coordinate system fixed to our reference frame as we observe this problem. But the little x, little y is a coordinate system physically attached to this ball. All right, so now one thing we have to realize here is that the coordinate system, this green set of coordinates, is moving along the circle. So this coordinate itself is actually rotating. Now we've got this velocity vector, velocity of A, which is like this, 8 meters per second. And this coordinate is going with it. We can actually calculate an angular velocity from that. Now we know that v is equal to r times the angular velocity, so that 8 meters per second is equal to this radius of curvature, 1 meter, times the angular velocity of this set of coordinates here. So what we get is that the angular velocity is 8 radian per second. And this is rotating counterclockwise, so that's going to be plus k direction. Now, A also has a tangential acceleration. It says something in the problem about it speeding up or slowing down. I've got to look here. It's okay. So this thing's decreasing at 6 meters per second. So that acceleration vector would go like this in that direction. That's a tangential. And because this has a tangential acceleration, that means this rotation rate that we've calculated is changing. And the relationship is going to be A equals R times alpha. So in addition here, we're going to have an angular acceleration of this set of coordinates as it goes around in this circle. And that is going to be, let's see, that tangential acceleration was 6 meters per second. That's this guy. 6 meters per second squared. And again, radius of curvature is 1 meter. That gives an angular acceleration of 6 meters per second. I'm sorry, not meter. Rad per second squared, and that acceleration is this way because, you know, take a look at this tangential acceleration vector. So the angular acceleration vector we could write as 6 rad per second squared minus k direction. Okay, so now when we write out a velocity equation for B with respect to A, let's see, velocity of B is equal to velocity of A plus velocity B with respect to A. All right, and the velocity of B is 7 meters per second plus I direction. And again, this is your problem here, so I'm not going to do all of this. Velocity A is 8 meters per second minus I direction. That's going to go here. This term is going to have a term due to the angular velocity crossed with the position here. So we're going to have a, let's see, this is going to look like negative 8 meters per second. This term here, we're going to have the angular velocity crossed with the position B with respect to A. Now, in addition to that, we're going to have a velocity of B with respect to A in the XYZ set of coordinates, in this green set of coordinates. And this would be the velocity that an observer on this ball would observe for this guy. So in effect, this is what we're looking for. Right? So again, these are values that we have, and then you basically would solve for this guy. To do the acceleration problem, we're going to have acceleration of B is equal to the acceleration of A plus, now here we got a couple things going on. Let me write it out. Acceleration b with respect to a plus acceleration b with respect to a in the xyz set of coordinates, again, which are moving along here. This green one is attached to this ball. And this is, again, what we're looking for in this problem. Now, the accelerations are two-dimensional beasts here, so let's go over here and talk about this. So b, let's see, what does it say about b? B has a velocity 7 meters per second shown, speed increasing at 4 meters per second per second. So we're going to have an acceleration vector that looks like this. That's a tangential, 4 meters per second squared. B is going to have a centripetal pointing upward, or a normal pointing upward, and here's how you can get at an expression for that. If I drew a position vector for this guy, it's equal to xi plus yj. Therefore, the velocity vector is x dot I plus y dot j. All right, so this is going to be x dot I plus y dot we can get from this function. That's going to be 2x x dot j. Therefore, the acceleration vector, and I'm going to get that by differentiating this, is going to be x double dot I plus twice. Now, when we differentiate this, we're going to get x dot squared plus x double dot j. Now, the good news here is that this is at x equals 0, so this term will be gone. And you'll have x double dot I, there's your 4 meters per second squared plus I direction plus 2x dot squared. Will give you the j component. There's the centripetal acceleration of this animal. Okay, this is acceleration of b. Acceleration of a, you can get from, let's see here, we're going to have this tangential acceleration to the right, and I think they gave us a numerical value for that. Yeah, 6 meters per second squared for this guy. In addition to that, we're going to have a centripetal down, so this would be plus I. And then your centripetal is going to be a v squared over r term. That's going to be an 8 meters per second squared over 1 meter, and that's in the minus j. So when you write out your acceleration equation here, we're going to have acceleration of b, oops, I guess I did that over here. Acceleration of b, which is going to be this term, is going to equal acceleration of a, which is this term, plus acceleration of b with respect to a. Now there's a couple things going on. Remember, we've got a coordinate system that has an angular velocity. So we're going to have an omega cross v term. That's going to be the angular velocity of this coordinate system crossed with the velocity vector of b. Okay, that would be this guy. Okay, but in addition to that, we're also going to have an alpha cross r term for the fact that this coordinate system has a tangential acceleration as well. So this guy's got, you know, two things going on, and then you can solve for this animal. So that should be enough to get you through with this problem. I think I'll end this video here. Again, this was help with number 137. Have a great day.